Numerical Computation, Chapter 10, Video 4. We now take a look at nonlinear shooting. This will be pretty different from linear shooting. After we finish the nonlinear shooting, we will comment on its similarity and how it can be applied to linear shooting. In the end, linear shooting becomes just a special case of the general nonlinear shooting. Okay, we now have a general nonlinear second order ODE given like that, and with the two boundary conditions given at A and B. And we want to solve for y on the interval from A to B. So typically f here is a nonlinear function of y or y prime. And now let's denote y tilde to be the solution of the following initial value problem. So the same equation, but we're putting initial conditions. So y tilde at A is alpha, that's the original condition at A, we copy, and we make our guess of the y tilde prime at A, and we guess with the value z. And let's see what happens to the solution with this guess. So you'll see later that this guess will be a thing that we will adjust and iterate. So we see if we choose a different value of z, we will get a different solution for this initial value problem. So you can say for each z, there is a solution, which means the solution of 1 depends on your choice of z. So this clearly says to me that there is some kind of a mapping or function here. So in particular, the value at b in my solution y tilde depends on the choice of z I make. So let's denote this relation by a function phi. So there is some function phi which is nonlinear such that phi of z will give me the value y tilde at b. So we want that the y tilde satisfies in the end also the boundary condition for a specific choice of z. Okay, so I would like to have phi of z equals to beta. Moving the beta to the left-hand side, then I have phi of z minus beta equals to 0. And I need to solve this equation and find the value z. So remember, we had a nonlinear equation to start with, so the phi as a function of z typically is nonlinear. So this means we need to find a root for a nonlinear equation. How do we do that? Do we remember we learned it? If you are thinking of Newton's method, you're very close. So I would suggest using Secant Method and not Newton. Why? Well, for Newton's method, you need the derivative of your function. Here, you would need the derivative of this function, phi. And you know, phi denotes the relation between z and y tilde b. And we don't really have an expression for this function phi. We just know if you give me a z, I can do a computation to get y tilde of b. So it's very hard to find the derivative. Okay. And yet for secant method, you just need two starting points, z1 and z2, and then you can find the secant line. For that, there's no problem. So we're going to use the secant method. Okay, so here is how the algorithm will look like. So step 1, I will choose some initial guess. So I will need 2, so let's call it z1 and z2. And using that, I solve the initial value problem and I evaluate the solution at B, and I construct this function. I call it value phi1, and that will be the phi with z1. And putting in z2, I carry out the same computation and find the value of y at B, and I call it phi2. Then the next value for z3, could be computed by a secant step. So these three will be z2 plus what is available in the secant step. Okay, so beta minus phi2, how far away you are, multiplied by the inverse of the derivative, but this is computed using kind of a secant slope. So it's actually the slope will be phi2 minus phi1 over c2 minus c1. Thinks this will be in the denominator, so I write it here and I flipped it. Then you know z3 is a better choice, and then you can take z2 and z3 and go through the same process and get a z4, and then use z3 and z4 and get a z5. So you can iterate until you find some convergence criteria being satisfied. For example, you can say until you are close enough to the target, this distance is less than some tolerance. Or you can put some other stop criteria for secant iteration, which we talked about when we learned it. Okay, let's put some remark. So the nonlinear shooting method, as we see, it's actually more general than the linear one. The linear algorithm we presented would only work for a linear problem, but the nonlinear one, we see that it works also on linear problem. So in that case, all you need to perform is one secant iteration, and that's it, no matter what two initial guesses you choose. So in our presentation of the linear problem, we chose two initial guesses as 0 and 1, and we commented that it doesn't matter. Now we know it doesn't matter. There are extensions of this nonlinear shooting, say, to other types of boundary condition or higher order nonlinear equations. They can be done in a completely similar way as we did for the linear case. But the difference here would be you will have to adopt a secant iteration around the shooting, wrap it around so you can iterate. So I encourage you all to try and give it a thought and try to work out details of that on your own. Okay, hope you enjoyed this, and see you next time.